What is the biggest thing in the universe? For most of human history, this question felt almost unanswerable. Stars were once thought to be the ultimate giants. Then galaxies took their place. And for a time, it seemed reasonable to believe that nothing larger could exist. But in 1985, that assumption began to crumble. That year, a team led by John Huchra at the Harvard-Smithsonian Center for Astrophysics completed an ambitious survey of thousands of galaxies in the direction of the constellation Coma Berenices. The goal was straightforward map where galaxies were and how far away they lay. The results, at first glance, appeared unremarkable columns of positions, distances, redshifts, just data. Then someone looked at the pattern. As the points were plotted in 3 dimensions, something unexpected began to emerge. Across hundreds of millions of light years, galaxies were not scattered randomly through space. They traced long strands, dense knots, vast bridges of light, and slowly, almost reluctantly, a familiar shape appeared. It looked like a person, a towering stick figure stretched across the cosmos. A long, slender torso, outstretched arms, legs frozen mid-motion, as if dancing across the universe itself. This strange apparition was not a creature of myth, nor a trick of imagination. It was one of humanity's first clear glimpses of a supercluster, a structure so vast that it redefined what large meant in cosmology. And it was only the beginning. As surveys expanded, astronomers realized that the observable universe is filled with superclusters. Not dozens, not hundreds, but roughly 10 million of them, each one containing tens of thousands, sometimes hundreds of thousands of galaxies bound together by gravity across unimaginable distances. Even our own Milky Way is not alone. It resides within a supercluster called Laniakea, perched along one of its outer limbs, far from the dense heart of the structure, quietly orbiting within a vast cosmic flow. These superclusters are colossal. Even the smallest span several hundred million light-years, woven from branching filaments and dense clumps of galaxies that resemble a cosmic web, the largest stretch across the heavens for up to 10 billion light-years. Their immense volumes rivaled only by their mass. A typical supercluster can contain over 10 million billion suns worth of matter stars. Gas, dust, dark matter all moving together through space. The nearest superclusters are named simply after the constellations through which we observe them: Coma, Virgo, Hydra Centaurus, Pavo Indus. More distant ones usually receive only catalogue numbers, unless they break records of size or mass. One such exception is the King Ghidorah supercluster, discovered in 2022 by a team of Japanese scientists and named after the three-headed nemesis of Godzilla. It is one of the most massive structures ever mapped, a fitting name for a cosmic monster. And yet, despite their staggering scale, despite their ability to bridge galaxies across billions of light-years, superclusters are not the largest things in the universe, because there exists something far larger, far more dominant, and far more unsettling. The true largest objects in the universe are not things at all. They are nothing. They are not titans of ancient legend, nor Kaiju of modern cinema. They are the opposite shadows in the dark, for most of the universe is not filled with light, or stars, or galaxies. Most of it is empty. These vast regions, known as cosmic voids, contain almost no matter at all, no glowing filaments to trace their boundaries, no gas clouds to reveal their shapes. They can only be detected by what is missing. And yet, cosmic voids are the largest structures in existence. They define where superclusters can form. They define the architecture of the cosmic web. They define, in a very real sense, where we are allowed to exist. Our solar system, our galaxy, our supercluster, all of it hangs suspended along the edges of these immense abysses. And in the far future, they may be the ultimate destiny of everything in the universe. Long before we could see them, theorists suspected their existence. The first computer simulations of the universe, run in the 1,960 seconds, were simple n-body simulations, capable of tracking only about 100 particles at a time, crude by today's standards, barely a shadow of reality. Compare that to modern simulations like Flamingo, which model hundreds of billions of elements, capturing the growth of cosmic structure in extraordinary detail. These simulations reveal a universe not filled uniformly with matter, but carved into filaments, clusters, and vast, expanding voids. The universe, it turns out, is not built around what exists, but around what does not. And it took human beings staring at faint points of light, night after night, to realize that the greatest structures of all are defined by absence. This is where our story truly begins. As new galaxies were added to their survey, Thompson and Gregory faced a problem of presentation. Thousands of data points, positions, distances, redshifts were useless if no one could see the pattern they formed. Their solution was deceptively simple, yet quietly revolutionary. They plotted the galaxies as a thin slice of space, shaped like a slice of pizza. Earth sat at the narrow tip of the slice, while distance expanded outward toward the crust. As galaxies lay farther from us, the diagram widened, allowing their distribution to be seen at a glance. At first, the idea seemed almost trivial, but in practice, it changed everything. For the first time, astronomers could visualize the large-scale structure of the universe in a way that compressed immense amounts of information into an intuitive, readable form. The plan for the survey was modest. Thompson and Gregory aimed to map galaxies in and around the Coma cluster, long known as a dense concentration of galaxies. By doing so, they hoped to compare galaxies inside the cluster with those in the surrounding field. The supposedly random background population thought to fill the universe more or less evenly, but what they found was not a subtle statistical difference. They found nothing. On the pizza-shaped plot, the Coma cluster appeared exactly as expected, a dense knot of black points. Around it, scattered galaxies dotted the diagram, and then, stretching across the plot like a silent wound, was a vast region with no points at all, a space millions of light-years wide that should have been filled with galaxies but wasn't. The new plotting technique made the absence impossible to ignore. The void was not subtle. It was not a gap that could be explained away by noise or incomplete data. It was a clean, unmistakable emptiness carved directly into the structure of the universe. Thompson and Gregory gave this blank region a simple name, a void. When their results were published, the reaction from the astronomical community was swift and hostile. Many astronomers rejected the finding outright. "We have already taken the measure of the heavens," critics argued. Galaxies, they insisted, filled the cosmos everywhere. If Thompson and Gregory saw nothing, then something must be wrong. Perhaps there was a flaw in the survey design. Perhaps the amplification technique introduced bias. Perhaps the astronomers were seeing what they wanted to see. After all, nature abhors a vacuum. A void of this scale should not exist, and therefore could not exist. But while skepticism dominated Europe and America, something remarkable was happening elsewhere. Only months after Thompson and Gregory released their findings, a group of Estonian and Soviet astronomers and theorists published the results of an entirely independent survey, conducted in a different region of the sky. They did not use the pizza slice diagram, yet they reported the same conclusion. Large holes existed in the distribution of galaxies, and unlike their Western counterparts, these scientists were not surprised. In fact, they had been actively searching for such structures. The difference lay in theory. In the West, the dominant cosmological paradigm insisted that the universe was homogeneous on large scales. While clusters of galaxies were known to exist, they were thought to be nothing more than dense fluctuations within an otherwise random, uniform distribution. Voids simply did not fit this picture. But in the Soviet Union, a radically different model had taken hold. The great theorist Yakov Zeldovich had proposed that cosmic structure formed through a process of fragmentation. In his model, vast regions of matter collapse and splinter over time, breaking into sheets, then filaments, then clusters, and finally galaxies. In such a universe, voids are not anomalies. They are inevitable. Empty regions naturally emerge as matter drains into denser structures, leaving behind enormous expanses of near-nothingness. For several years, the debate remained unresolved. Then, in 1981, American astronomer Robert Kirshner led a new survey in yet another direction of the sky. What his team found could no longer be dismissed. They discovered what is now known as the Boötes void. It was staggering. The Boötes void was larger than any galaxy, larger than any cluster, larger than anything else within the survey volume. At the time, it was the largest single structure ever identified, not a thing, but an absence, a colossal expanse of emptiness dominating the region of space it occupied. Together with the Coma void, the original void discovered by Thompson and Gregory, astronomers were forced to confront a new reality. Voids were real, but their existence raised profound questions. How could such vast empty regions form? And more troubling still, how could a supposedly homogeneous universe allow such enormous blemishes? These questions marked the birth of a new field, the study of the large-scale structure of the time. Universe. The old picture, an endless sea of galaxies with occasional clusters sprinkled throughout, collapsed. In its place emerged something far more elegant and far more strange. Clusters were still there, but they were no longer the main feature. They were nodes, dense knots, suspended within an immense cosmic web. Galaxies traced long, thin filaments stretching across space. Vast sheets and walls of galaxies spanned hundreds of millions of light-years, dwarfing anything previously imagined, and surrounding it, all larger than clusters, larger than walls, larger than superclusters themselves, were the voids. Immense regions of emptiness that define the structure of everything else. The universe, it turned out, was not built from matter alone. It was sculpted by absence. And in that realization, astronomers caught their first true glimpse of the cosmos as it really is. The voids, those immense expanses of apparent nothingness, were the structures that first defied expectation and then came to define the large-scale architecture of the universe. Once dismissed as errors or gaps in data, they soon demanded explanation. What became increasingly clear throughout the 1,980 seconds and 1,990 seconds was that the universe could still be homogeneous, but only on scales far larger than anyone had previously imagined. Clusters of galaxies, impressive as they are, did not represent the upper limit of cosmic structure. Even the smallest known cosmic voids utterly dwarf them. These voids were not isolated curiosities. They outlined and shaped a far grander framework, one that subsumed the entire observable universe. Mapping this structure, voids and clusters together, revealed a cosmic web of staggering scale. But with every new survey, every deeper look into space, cosmologists encountered an unsettling pattern. Void after void appeared, each rivaling or even exceeding the size of the Boötes and Coma voids. And with each discovery came the same haunting question. Is this finally the scale at which the universe becomes uniform? Or does homogeneity always lie just beyond the horizon of our measurements? That question, where structure ends, uniformity begins, remains unanswered. Humanity has faced similar uncertainties before. We do not know who crafted the Lennox globe, but we know when it was made, the year 1510. Less than 2 decades after Columbus's voyage connected the Old World and the New. The globe depicts Europe, Africa, and Asia, with coastlines that are recognizable yet wildly distorted by modern standards. South America appears, though only its southern half. North America is rendered as a scattering of large islands. Australia and Antarctica are nowhere to be found. And along the eastern coast of Asia, partially known at the time through second-hand accounts from sailors, A phrase is inscribed in Latin: hic sunt dracones. Here be dragons. The Lennox globe is one of only 2 surviving maps known to contain that exact phrase. But the sentiment was widespread in medieval cartography. The world was opening to exploration, trade, and conquest. With every voyage, geographers learned more, but vast regions remained unmapped. Faced with blank spaces, mapmakers made a choice. They filled the unknown with dragons, tuar serpents, lions, and monstrous creatures, not merely as decoration, but as warnings. Beyond the edges of the known world lay mystery, danger, and the unknown. That sense of lurking uncertainty did not vanish with the age of exploration. It followed us into the heavens. As astronomers pushed farther into space, they too encountered blank regions, boundaries not of geography, but of knowledge. Our maps of the universe still begin with what is familiar, named, and seemingly safe. The solar system, a single star orbited by 8 planets and countless smaller bodies. Yet this entire system is just one among hundreds of billions within the Milky Way. Our galaxy, with its graceful spiral arms and dense central core, spans roughly 100,000 light-years in diameter, though it is less than 30,000 light-years thick. Compared to that scale, even the farthest reaches of the solar system are microscopic, no more significant than a single cell within a human body. Some 5 million light-years away lies our nearest major galactic neighbor, Andromeda. It contains up to 1 trillion stars and shines as a magnificent spiral in its own right. Together with the Triangulum galaxy and dozens of smaller dwarf galaxies, it forms what we call the local group. The name is uncreative, but accurate. A modest collection of galaxies bound together by mutual gravity. Whatever fate awaits the universe, these galaxies will face it together. Beyond the local group, the next major structure we encounter is a cluster, specifically the Virgo cluster, named for the constellation through which we observe it. Galaxy clusters are the largest gravitationally bound structures in the cosmos. Dense metropolitan hubs containing thousands of galaxies and spanning millions of light-years. The Virgo cluster lies about 65 million light-years away. And at this distance we truly enter the realm of cosmology. Virgo is not alone. It sits at the heart of a supercluster, an even larger aggregation of matter. Superclusters are the largest known concentrations of galaxies in the universe. Though they are not fully gravitationally bound, their internal gravity has not yet overcome cosmic expansion. They are still forming, still evolving. Our home belongs to one of these vast entities, known somewhat confusingly as the Virgo supercluster. The repetition of names reflects the historical layering of discovery rather than clarity of structure. The Virgo cluster is merely the dense core of a far larger, sprawling system. And beyond even these immense structures, beyond clusters and superclusters, lie the voids. Vast regions where galaxies are scarce or entirely absent. Enormous cosmic blank spaces that do not merely interrupt the universe's structure, but define it. Like the dragons of ancient maps, they mark the limits of what we know, reminding us that every time we chart new territory, the unknown simply retreats farther into the distance. The universe, it seems, still has many blank spaces left. At the heart of the Virgo supercluster lies a complex and bustling structure, home to dozens of galaxy groups, much like our own local group. For a long time, astronomers believed this was the full extent of our cosmic neighborhood, but more recently, a profound realization reshaped that view. The Virgo supercluster itself is not an isolated giant. It is merely one limb of an even greater structure, an immense supercluster, now known as Laniakea, a name drawn from the Hawaiian language meaning immense heaven. The name is fitting. Laniakea is vast beyond easy comprehension. It contains 4 enormous branches, each one large enough to qualify as a supercluster in its own right. Within its tangled structure lie up to 500 individual galaxy groups and clusters, encompassing well over 100,000 galaxies in total. These galaxies are not scattered randomly. They form a vast, branching network of matter stretching across more than 500 million light-years of space. To grasp its scale, imagine comparing a single galaxy to Laniakea itself. The difference is roughly equivalent to comparing a single person to an entire city, but that analogy still falls short. Each galaxy contains tens, sometimes hundreds of billions of stars. In that sense, Laniakea is not merely a city, but a colossal metropolis, a cosmic megacity housing quadrillions upon quadrillions of stars. Its stellar population rivals, in sheer number, the total number of ants living on Earth, and Laniakea is not alone. Beyond our home supercluster lie others just as imposing: the Hercules supercluster, the Shapley supercluster, the Perseus-Pisces supercluster. Beyond these, the number of known superclusters grows so large that astronomers can no longer assign poetic names to each one. Instead, they are catalogued numerically, entries in vast computer databases that record their positions in space and list their countless member galaxies. Taken together, all of these interconnected superclusters form something far greater than the sum of their parts. They create the cosmic web, the largest known structure in the entire universe, spanning the observable cosmos. Nearly 95 billion light-years across this immense network fills every corner of space with filaments, walls, and nodes of matter. Supercluster connects to supercluster through long, thin filaments of galaxies. Where these filaments intersect, massive galaxy clusters like Virgo emerge. Broad, sheet-like walls of galaxies stretch across space, partitioning the universe into vast regions. The scale of the cosmic web defies ordinary analogy. One might say that individual galaxies relate to the cosmic web the way cells relate to the human body, but for that comparison to truly work, each cell would need to be 1,000,000 times smaller than it actually is. The web is simply that vast. Individual galaxies, each stretching over 100,000 light-years and containing hundreds of billions of stars, appear as little more than tiny points of light embedded within this colossal structure. Yet, as dazzling and incomprehensibly enormous as superclusters and filaments are, they occupy only a small fraction of the universe by volume. By far, most of the cosmos is void. Nearly all galaxies, except those buried deep within the dense hearts of clusters, live on the edge, never far from immense gulfs of relative nothingness. In this sense, the term cosmic web is strikingly appropriate. Just as the threads of a spider's web catch the eye but occupy almost no space, so too do galaxies illuminate the filaments and clusters while being utterly dwarfed by the emptiness between them. Mapping these voids is surprisingly difficult, especially the ones closest to us. They are so vast and so empty that only the largest, most comprehensive surveys can reveal their boundaries. Still, astronomers know that the nearest void to the Milky Way is the local void, which by itself spans nearly 200 million light-years. Beyond it lie the northern and southern voids, the giant void, and the famous Boötes and Coma voids. As cosmological surveys continue to probe deeper into space, even more voids appear, arranged irregularly between and among the superclusters like dark hollows in the cosmic landscape. Despite their name, these voids are not perfectly empty. Early astronomers were astonished to discover that a few galaxies do exist within them. In addition, there are countless microscopic constituents, stray hydrogen and helium atoms, cosmic rays racing through space, elusive neutrinos passing unnoticed, and the ever-present glow of the cosmic microwave background. Yet the density of matter within a void is extraordinarily low. Cosmologists typically define a cosmic void as any region where the density of matter is less than 20% of the cosmic average. And the cosmic average itself is already sparse, roughly 1 hydrogen atom per cubic meter of space. By comparison, Even the most diffuse galaxy is millions of times denser than this average, deep within the heart of a void. Aside from the occasional wandering atom or passing particle, one can find oneself millions of light years away from any significant structure. No galaxy, no star, nothing but darkness. These are, by far, the loneliest places in the universe. Remarkably, voids are not just empty of ordinary matter, they are also largely empty of dark matter. Dark matter makes up more than 80% of the mass of nearly every galaxy and cluster in the universe. Despite being completely invisible and composed of particles still unknown to modern physics, this dominance extends throughout the filaments and walls of the cosmic web. The galaxies we observe are merely bright lighthouses, marking the peaks of a far larger, invisible structure. The cosmic web itself is sculpted by dark matter. Where dark matter is densest, galaxy clusters form. Where it stretches into long strands, filaments of galaxies follow. And where dark matter is absent, deep in the largest cosmic voids, galaxies fail to form at all. Although we cannot directly observe dark matter through light, cosmological simulations reveal its structure in stunning detail, exposing the hidden skeleton upon which the visible universe is built. Large galaxy surveys, such as the Sloan Digital Sky Survey, have already identified tens of thousands of cosmic voids. Even so, this represents only a tiny fraction of the observable universe. The smallest voids are about 20 million light-years across and are often found embedded within much larger concentrations of matter, small pockets of emptiness nested inside even grander structures. And beyond them lie voids so vast that their full extent still eludes our measurements. Together, these immense empty regions are not mere gaps in the universe. They are its defining feature. Pockets of emptiness can be found buried even within superclusters themselves. But the largest voids stretch across truly staggering distances. Some span significant fractions of the known universe, separating their surrounding superclusters by distances of 1 billion light-years or more. And it is within these immense regions of nothingness that a potential problem begins to emerge. Voids are vast and empty, a fact that once surprised astronomers but is now broadly understood within modern cosmology. We know how voids and the brightly illuminated superclusters form together over billions of years of cosmic evolution. Yet certain observations hint that the very largest voids may be too large, so large that they appear to strain or even challenge our current understanding of the universe. These are the so-called supervoids, structures so immense that their very existence raises uncomfortable questions. To understand why, it helps to step back from the cosmos and consider an analogy much closer to home. The entrance was hidden in the bottom corner of a sinkhole, completely concealed from above and discovered entirely by accident. A local Vietnamese logger, searching for wood near the border with Laos, heard the sound of rushing water. Curiosity drew him closer. The opening was pitch black, but he later recalled that the air itself told him he was stepping into something vast. A powerful wind rushed outward, as if from an underworld cavern. He retreated, unable to find the entrance again, and it remained lost for nearly 20 years. In 2008, the cave was rediscovered. The following year, Ho Khan guided the British Cave Research Association into the darkness. Over multiple expeditions, explorers slowly revealed the full extent of the system. It stretched for nearly 10 kilometers. The cave, called Sun Dung, meaning Cave of the Mountain River, turned out to be the largest cave in the world. It contains its own ecosystem, its own weather, and had spent millions of years hidden in plain sight, undisturbed beneath the surface of the Earth. Our world, it turns out, is full of hidden wonders, vast empty spaces lingering undiscovered just beneath our feet. And so the question naturally arises, what else are we missing in the universe? What caves? What empty regions? What unseen structures lurk in the immense reaches of the cosmos? And what can these cosmic caverns teach us? Cosmic voids and supervoids lie between and among the greatest structures in the universe, and we have only just begun to explore their unsettling depths. Despite their universe-dominating scale, these voids were not always so large. Like their counterparts, the walls, filaments, and clusters of galaxies' voids began their existence as minuscule fluctuations in the quantum foam that permeates all of space and time. These fluctuations were briefly frozen during the violent epoch of cosmic inflation, a hypothesized event that occurred when the universe was less than a second old and expanded space by many orders of magnitude. What began as subatomic variations in spacetime were stretched into tiny differences in density across the early universe. From that point onward, gravity took over. Regions with slightly stronger gravitational pull began to attract matter. As matter accumulated, gravity intensified, allowing these regions to draw in even more material from their surroundings, like a small stream slowly carving a cave into solid rock. Gravity worked patiently, but relentlessly, over hundreds of millions of years. This process built the cosmic web. The first stars ignited. The first galaxies formed. Those galaxies gathered into groups. Then clusters. Wispy, thread-like filaments emerged, funneling matter into growing nodes of mass. Massive clusters took shape at the intersections of these filaments, bright and dense. But in the universe, when the rich get richer, the poor inevitably get poorer. As matter flowed into galaxies, groups, and clusters, it had to come from somewhere. It came from the voids. Voids began as barely perceptible depressions in density differences of only 1 part per million compared to their surroundings. At first, they were almost indistinguishable from any other region of space. But as matter drained away from them and into the growing structures nearby, they emptied out and expanded. While galaxies and clusters grew through violent mergers and dramatic collisions, voids lived quiet, uneventful lives. They simply grew larger. At first, this growth was slow. Then, as the gravitational pull of the cosmic web strengthened, it accelerated over the same hundreds of millions of years that witnessed the birth of the first stars and galaxies. The first voids also emerged tiny, forgotten pockets that steadily increased in volume until they came to dominate the universe by sheer size. Voids can merge, much like galaxies and clusters do. But the process is far less dramatic. If a wall of galaxies separates 2 neighboring voids, the galaxies within that wall gradually drift away over time, pulled toward denser clusters at the wall's edges. As enough material leaves, the wall dissolves, and the 2 voids become one larger entity. There is no titanic collision, no release of vast energy, only the slow, inevitable expansion of nothingness. This fluid behavior made voids notoriously difficult to define. Where does one void end and another begin recently? Cosmologists found an elegant solution. Inspired by an entirely different discipline, geography, geographers often seek to understand how water moves across land. To do this, they create watershed maps, dividing landscapes into regions where all water flows toward the same destination. Watersheds are separated by high topographical features like mountain ridges, pour rain over a continent, and some water flows toward one ocean, some toward another. The mountains define the boundaries. Cosmologists applied this same idea to the universe. If dense regions like clusters, walls, and filaments are treated as cosmic high ground, then voids become the basins into which matter flows away. In this framework, a void is defined not merely by its emptiness, but by the direction of gravitational flow around it. Through this lens, voids are no longer vague absences. They become well-defined regions of cosmic drainage, immense basins carved not by water, but by gravity itself. If we imagine the dense filaments and walls of galaxies as towering mountain ranges, then the low-density cosmic voids become the vast valleys between them. With that analogy in place, cosmologists can perform a similar kind of analysis to what geographers do on Earth. Picture rain falling uniformly across the entire universe. Matter flows away from the high peaks of clusters and filaments and drains into the deepest valleys of emptiness. This watershed technique gives cosmology a powerful and unambiguous definition of a void. A cosmic void is simply a low-density region of the universe, defined not by what it contains, but by the surrounding topology that determines where matter flows, just as terrestrial watersheds are defined by the mountains and ridges around them. Using this method, cosmologists have been able to exploit massive galaxy surveys, such as the Sloan Digital Sky Survey and the Darkenergy Survey, to map and catalogue tens of thousands of voids in the nearby universe. And as these maps grew more detailed, a surprising pattern emerged. Voids themselves form a hierarchy. The largest voids are not perfectly empty. Within them exist small collections of faint, red galaxies. These galaxies are not scattered randomly. Instead, careful analysis reveals that even inside voids, matter organizes itself into a miniature cosmic web, thin filaments, tiny groups, and sparse nodes. And between these tenuous structures lie even emptier regions, voids within voids. Imagine an enormous cave system. A vast central chamber opens into smaller caverns, separated by thin rock walls, which themselves contain narrower tunnels and pockets of emptiness. This is what cosmologists are finding in the universe. Simulations of the cosmic web reveal even deeper layers, subvoids nested inside voids, which are themselves nested inside larger voids. The structure appears fractal-like, repeating the same patterns across multiple scales. However, we cannot observe this hierarchy in its entirety. Most of the cosmic web exists not in luminous galaxies, but in dark matter, invisible to our telescopes. Galaxies only trace the brightest outlines of a far deeper structure beneath. And this raises a profound question. Where does the hierarchy end? Are the largest known voids, such as the Bootes void, the ultimate limits of emptiness, or are they merely subvoids inside even larger expanses of nothing? Clues to the answer come from an unexpected source, the cosmic microwave background, or CMB. The CMB is the afterglow of the universe when it was just 380,000 years old. At that time, the universe was 1,000,000 times smaller than it is today and blisteringly hot around 10,000 Kelvin, forcing all matter into a dense plasma. As the universe expanded, it cooled. Atoms formed, space became transparent, and light, once trapped, flooded the cosmos. That radiation still surrounds us today as a faint microwave bath. The CMB is remarkably uniform, but not perfectly so. It contains tiny temperature variations, about 1 part in a million hotter and colder spots of different sizes. These fluctuations encode immense information about the early universe. Cosmologists understand their statistics with extraordinary precision, except for one. There exists a region of the CMB known simply as the cold spot. It is unusually large, unusually cold, and so extreme that standard cosmological models struggle to explain it. Theories have ranged from radical revisions of physics to the exotic possibility that the cold spot marks a collision between our universe and another. But the most likely explanation is far less fantastical and far more unsettling. The cold spot may be the imprint of a supervoid. When CMB photons first entered this region billions of years ago, the void was smaller and shallower, but the void is so immense that it took hundreds of millions to billions of years for the light to cross it. During that time, the void expanded and deepened. By the time the photons emerged, they had to climb out of a much deeper gravitational depression than when they entered. That energy loss left an observable signature, a cold spot in the CMB. This structure is now known as the Eridanus supervoid, and it is not alone. Another vast emptiness, the Karol-Hazy-Vajoni void, also called the giant void, lies over 1.2 billion light-years away and stretches across 1.3 billion light-years in diameter. But the most controversial of all was proposed in 2013. Astronomers Ryan Keenan, Amy Barger, and Lennox Cowie suggested the existence of an even larger structure, the KBC void, sometimes called the Great Local Void. This hypothetical void could span up to 3 billion light-years. Its volume would be so vast that it could contain superclusters like Laniakea and Shapley and still qualify as underdense. The KBC void was proposed to help explain discrepancies in measurements of the Hubble constant, the present expansion rate of the universe. Measurements from the early universe, using the CMB, differ from measurements in the nearby universe using supernovae, because voids expand faster than denser regions. Living inside a massive supervoid could bias local measurements. Yet despite its explanatory power, the KBC void remains highly disputed, lacking independent confirmation. Even without it, the existence of other supervoids already pushes cosmology to its limits. According to our best models, the universe should become statistically homogeneous on scales larger than about 300 million light-years. Beyond that scale, every region should look roughly the same. On average, supervoids challenge this assumption. To understand why, imagine measuring population density on Earth. Small regions vary wildly, cities, deserts, mountains, but make the region large enough. And every sample contains a mix of everything. That is homogeneity. Supervoids are like deserts, larger than the scale where deserts should no longer exist. If such structures are real, then either they are rare statistical flukes or our understanding of the universe's structure is incomplete. And this brings us back to the cave. Just as Sundong Cave existed for millions of years, vast and hidden, undiscovered beneath the forest floor, cosmic voids may hide in plain sight, immense regions of nothingness shaping everything around them, influencing light, expansion, and structure, yet remaining difficult to detect precisely because they contain so little. Voids began as tiny imperfections in the early universe, quiet, nearly invisible depressions. Over time, gravity drained matter from them. They grew, they merged, they expanded, not through violence, but through neglect. The universe built its greatest structures by emptying out its deepest spaces. And if the largest voids truly exceed the scale of homogeneity, then they are not merely features of the universe. They are tests of cosmology itself. Just as medieval maps once marked the unknown with dragons, modern cosmology now confronts vast blank regions where theory strains to follow observation. These cosmic caves remind us that the universe is not only defined by what shines, but by what does not. And in those immense, silent expanses of nothing, the universe may be telling us that we have not yet reached the end of the map. Are these colossal voids nothing more than rare cosmic accidents, statistical flukes that do not meaningfully disturb our understanding of cosmic homogeneity, or are they so immense that they force us to reconsider how the largest structures in the universe form, evolve, and ultimately decay? The question remains unsettled. Just as a cave on Earth that is too vast or too deep can challenge our understanding of geology, supervoids pose a similar threat to cosmology itself. Within the scientific community, there is no firm consensus. Some cosmologists argue that the largest known supervoids are simply too big to be reconciled with our current models. They appear to violate the expected scale at which the universe should become uniform, compelling us to rethink the foundations of cosmology. Perhaps an unknown fifth force of nature is at work. Perhaps some new component of the universe, still undiscovered, has shaped these enormous regions of emptiness. Others, however, point to increasingly sophisticated simulations of cosmic structure formation. These models suggest that, given enough volume and enough time, the universe should naturally produce the occasional supervoid even in our own cosmic neighborhood without breaking any fundamental rules. The debate remains unresolved, but one conclusion is unavoidable. The voids have not stopped growing. They were born billions of years ago as barely perceptible depressions in density, tiny irregularities embedded in an otherwise uniform sea of matter. Over cosmic time, they expanded relentlessly, draining matter from their interiors and pushing it toward the surrounding filaments, walls, and clusters. Today, voids dominate the universe by volume, and in the coming billions of years, they will continue to grow, tearing apart the cosmic web itself, leaving behind a universe increasingly defined not by structure, but by darkness. There are many dangers in the cosmos. Many processes seek to grow, expand, and consume. On Earth, biological threats like viruses and bacteria are constrained by limited resources and competition. But on the largest scales imaginable, there is nothing to limit expansion, no competition, no resistance. The cosmic voids are not merely empty holes in the distribution of matter. They are dynamic entities. They were smaller once. They are not finished growing. And in a strange twist of physics, there is nothing that can ever truly stop them. We live in an expanding universe. With every passing moment, space itself grows larger. Another way to say this is that the average distance between galaxies increases over time. While local mergers still occur, such as the Milky Way's inevitable collision with Andromeda in roughly 5 billion years on sufficiently large scales, expansion dominates. In the late 1990 seconds, astronomers made a discovery that transformed cosmology forever. The expansion of the universe is accelerating. To this day, we do not know exactly why. We call the cause dark energy. In the simplest models, dark energy is treated as an intrinsic property of space-time itself. Even if you were to remove every particle, every photon, and every trace of matter from a region of space, that space would not be truly empty. It would still contain dark energy. This energy exerts a weak but persistent repulsive gravitational effect. In regions of high-density galaxies, clusters, filaments, its influence is overwhelmed by gravity, but averaged across the vast emptiness of the universe, dark energy becomes dominant, and there is one place where its power reigns supreme: the cosmic voids. These immense regions are empty of matter and radiation, but they are filled completely with dark energy. In a sense, voids are the perfect breeding ground for cosmic acceleration. It is within them, not within galaxies or clusters, that the expansion of the universe accelerates most strongly. Void interiors do not merely expand passively as matter collects along their edges. They actively push outward. They press against their boundaries. They thin the walls between neighboring voids. They stretch and strain the filaments of the cosmic web, weakening them over time. This process will not slow down. It will intensify. As the universe expands, there will be more dark energy. As dark energy becomes more dominant, it will drive expansion even faster. About 5 billion years ago, dark energy began to overtake matter as the primary driver of cosmic evolution. That moment marked the beginning of the end for large-scale structure formation. The grand story that began with tiny quantum fluctuations during inflation leading to the first stars, the first galaxies, and the vast cosmic web entered its final act. Something fundamental changed. The great superclusters, sprawling across hundreds of millions of light-years, will never fully collapse into unified structures. The voids surrounding them will continue to grow, crushing the delicate gravitational connections that bind clusters together. Matter will be driven farther and farther apart. Filaments will snap. Walls will dissolve. In only a few billion years, the cosmic web itself will be torn apart, not by violence, but by relentless expansion. The universe will not end in fire or collapse. It will unravel into emptiness. In that future, galaxies beyond our local group will slip beyond the cosmic horizon, their light stretched and extinguished by accelerating space. One by one, the great structures of the universe will fade from view. The voids, once subtle features in a young cosmos, will become its defining reality. And what began as tiny imperfections in the fabric of space-time will ultimately consume everything, leaving behind a universe dominated not by matter, not by light but by the silent, ever-expanding depths of nothingness. The cosmic voids are not merely the absence of structure, they are the future of the universe itself. No more filaments, no more superclusters, no more vast walls of galaxies stretching across the sky. In the far distant future, only isolated groups and lonely clusters will remain, scattered like fading embers across an ever-expanding ocean of absolute emptiness. The universe will belong to the voids. They will win, not through violence or destruction, but through patience, through the quiet, unstoppable growth of nothingness itself. As the voids expand, they will erase the great cosmic structures that once defined the universe, leaving behind a darkness so complete that even memory seems to dissolve within it. And yet, in a profound irony, these same voids destined to dominate the future are also humanity's clearest windows into the deepest past. When cosmologists attempt to understand the universe, they are left with only two fundamental approaches. One is to seek direct observational evidence from specific epochs in cosmic history, such as the cosmic microwave background. The CMB is a priceless relic, a snapshot of the universe when it was just 380,000 years old. But it is also fundamentally limited. It was created in a single brief moment and carries only a finite amount of information about that early time. The second approach is broader, slower, and more ambitious. Cosmologists observe as much of the modern universe as possible, mapping the distribution of galaxies, groups, clusters, filaments, and voids across immense volumes of space. Using these maps, combined with the known laws of physics, they attempt to rewind cosmic history, reconstructing how the universe evolved and what it is made of. The contents of the universe, ordinary matter, dark matter, and dark energy, determine how the cosmic web forms and changes. A universe dominated too strongly by dark energy would never have formed galaxies at all. A universe lacking sufficient dark matter would have produced only fragile, underdeveloped structures. The entire story of cosmic evolution is written into the architecture of the cosmic web. It is a vast archive, holding clues about the universe's composition, its history across billions of years, and its ultimate fate. But the cosmic web is staggeringly complex. In principle, one could trace every galaxy, every cluster, back to the primordial mixture of hydrogen and helium that filled the universe shortly after the Big Bang. After all, the universe is ultimately just particles interacting through physical laws. But in practice, this is nearly impossible. Your own body contains trillions upon trillions of hydrogen atoms. Those same atoms have existed for over 13 billion years. In their positions, emotions, and interactions lies an unimaginably faint echo of the early universe. Yet reconstructing that history would require tracking every interaction those atoms have undergone across cosmic time, an impossible task. The same is true of galaxies and clusters. They are chaotic, dynamic systems shaped by star formation, magnetic fields, cosmic rays, supernova, explosions, black holes, and countless overlapping physical processes. Their complexity buries the primordial information we seek beneath layers of evolution. The voids, by contrast, are simple. They are empty. They are clean. They are quiet. They are, in a sense, boring. And that is precisely what makes them invaluable. Cosmic voids have changed very little over billions of years. They have grown larger and occasionally merged with neighboring voids. But these processes are slow, gentle, and orderly. Compared to galaxies and clusters, voids are remarkably unevolved. They preserve a clearer imprint of the universe's initial conditions. If we want to understand what the cosmos was like long ago, the voids are where we should look. Even more importantly, voids are filled with dark energy. Although dark energy permeates all of space-time, it is almost impossible to study within dense regions like galaxies, clusters, or planetary systems. In those environments, the gravitational influence of matter overwhelms everything else. The dynamics are too complex, too noisy, to isolate the subtle effects of dark energy. But not in the voids. The voids are dominated by dark energy. They are natural laboratories, vast, pristine regions where cosmologists can study the behavior of the universe's most mysterious component with minimal interference. Within them may lie the clearest clues to the nature of dark energy itself. For decades, cosmic voids were ignored. They lingered in the shadows of cosmology, dismissed as uninteresting gaps between the real structures of the universe. Their initial discovery was even mocked. Many astronomers simply could not believe that the universe could produce regions of such staggering emptiness. That attitude has changed. Over the past decade, interest in cosmic voids has exploded. New techniques, such as watershed algorithms, have allowed scientists to identify and define voids reliably within large galaxy surveys. And as those surveys have grown in scale and precision, cosmologists now have not just a few voids to study, but thousands. The European Space Agency's Euclid telescope, launched in 2023, is now mapping the positions of millions of galaxies across a vast portion of the sky, where void research was once a niche pursuit on the fringes of cosmology. It has become a central field of study. Entire research teams are now dedicated to finding, cataloging, and analyzing cosmic voids, because in the emptiest places in the universe, we may finally find the deepest answers about where we came from, what the universe is made of, and how it will one day fade into silence. Cosmic voids are now being systematically identified within modern surveys and used as precision tools to probe the nature of dark matter and dark energy themselves. The same focus extends to NASA's next flagship mission, the Nancy Grace Roman Space Telescope, which includes a dedicated working group devoted entirely to the study of these vast, empty regions. What was once considered irrelevant nothingness has become one of the most promising frontiers in modern cosmology, and with every passing year, the universe seems to be teaching us the same quiet but profound lesson. If we truly want to understand the deepest mysteries of existence, if we want to test the limits of our theories, challenge our assumptions, and push beyond the boundaries of known physics, then we must learn how to look where almost nothing exists at all. We must learn how to stare into the abyss, not with fear, but with curiosity, because it is in the deepest emptiness that the universe speaks most clearly. In the voids, complexity falls away, noise disappears, and what remains is the raw structure of reality itself, dark matter shaping the cosmic web, dark energy driving the expansion of space, and the faint imprint of the universe's earliest moments preserved across billions of years. The story of the cosmos is not written only in blazing stars or massive galaxies. It is written just as powerfully in absence, in the spaces between, in the regions where matter retreated, leaving behind the clearest record of how everything began and how everything may one day end. You have been watching the entire history of the universe. If you found this journey meaningful, don't forget to like, subscribe, and share your thoughts in the comments below. Thank you for watching.